But this is an ellipse, and I've got this little thing up here on a smartboard. And you've got ellipses, they do have a center, but part of the definition of ellipse is these 2 points right here that we call foci. Because an ellipse is kind of like when you take 2 parabolas and weld them together in the middle, okay? But they have 2 foci. And I know it's kind of hard for you to see here, but what is happening here is this red distance, which is from the foci to the ellipse, and this blue distance from that foci to the ellipse are being added together. And what stays the same? The total distance. It's part of the definition of an ellipse. So when you start talking about the definition of an ellipse, you talk about that fact right there, because that's something that holds true for all ellipses. You can't just say it's a shape that looks like an egg. It doesn't work in math. Right? It just doesn't work. So math needs very precise definitions. An ellipse is the set of all points whose sum of distances from 2 foci is constant. Like in that example, let's say 10. The whole time it was always 10. So the sum of the distances from 2 foci is constant. That's the mathematical definition. They're really not any harder than yesterday. We just have different forms that we use. So that's the deal, different forms. You identify your parts and use a proper form to do them. So we'll start with ellipses that are focused or centered at the origin. And the major axis is the x-axis. What that means is it's kind of parallel to the x-axis. You kind of see how the x-axis is the line of symmetry. Cuts it right in half. Do you guys see that? Major axis, the x-axis, that means line of symmetry. Or x-axis is line of symmetry. So we're going to have a center at 0, 0, the origin. And the diagram kind of gives us a clue as to what our foci are. Most texts teach the foci as negative C0 and C0. The lettering is kind of important because there's some forms that we use. So you have 2 foci at negative C0 and C0. C is foci, okay? Focus on the C in foci. C for foci. It's not that hard. Vertices, we use these guys right here along the major x-axis at negative A0 and at A0. Now, there's an equation, there's a form for this. The equation form itself is x squared over a squared plus y squared over b squared equal to 1. Some other details about here. A has to be greater than b. A is greater than b, and they both have to be greater than 0. Otherwise, this wouldn't be an ellipse. And there's a little bit of almost Pythagorean theorem here. Not quite Pythagorean theorem, but almost Pythagorean theorem. B squared is a squared minus c squared. Double check that real quick. I hadn't taught this since 2016. That's the last time I actually did any of it. Yeah, that's right. Well, don't look so excited. What? These? No, we can have it in the equation. That's a plus. No, the last thing on the end of the equation. 0. Well, don't look so excited about this. Y'all chose this. If you don't like this stuff, man, ellipses are used in all sorts of stuff. Heck, the transfer case on most vehicles is of an elliptical design. It's engineering 101. Can't build a motor without ellipses, plain and simple. Can't be done. Heck, there's a Wankel engine. It's called a Wankel engine. It was used in the Mazda, the R6s and R7s. It's kind of an interesting little engine. It doesn't have your typical pistons and stuff, but it uses ellipses in the entire design. You should look that up. It's not your typical engine with pistons that fire down. It literally rotates a large, almost gear-looking shape around an ellipse. Generates a ton of horsepower, very fuel inefficient, not a whole lot of torque, but it spins at really high RPMs. It's called a Wankel engine. It's pretty popular back in the 90s. All right, so task 1, find an equation of an ellipse. And this might be something you do. You might draw an ellipse. You've got foci and a vertex known. So this is kind of directly related to what you all will be doing. So this guy has a center at the origin. It has a focus at 3, 0. Now, if there's a focus at 3, 0, kind of look up here at that design. Where's the other focus? Negative 3, 0. They're equidistant from the center. And we have vertices at negative 4, 0. And there is a known vertex at negative 4, 0. If there's a known vertex at negative 4, 0, where's the other known vertex? 4, 0. It's just symmetry, kids. That's all it is. Now, what we have the major vertices, because major vertices are on the same line as the foci. We don't have what's called the minor vertices, the guys up here on the y-axis. It's cool, there's a formula for that. There is. What's it say b squared is? Yeah, and I'm talking about that because if you'll notice how these vertices are labeled, 0b and 0 negative b, that's how I get the other vertices. So I just use this formula. B squared is a squared minus c squared. Where do you get a? Does a come from the vertices or the foci? Vertices, because foci has a c in it, right? So b squared is 4 squared. You can pick on the 4, positive 4, negative 4. Nobody cares. Minus c squared. What's c squared? What is c? 3 squared. So we do a little 4 squared minus 3 squared. What do we get? 7. So b is plus or minus the root of 7, which is kind of hard to graph. It's a little over, what, 2? I'm not going to sit here and try and figure out what it is exactly. But I have a vertex here at 0, root of 7. These are called minor vertices. Another one at 0, comma, negative root of 7. I know it's over 2 because it's, the square root of 4 is 2 and square root of 9 is 3, so it's somewhere between 2 and 3. Can't see anything I just drew. So I'm actually doing the graphing before I do the equation, because it just made sense to me to do it that way. So there's my pretty little ellipse. You connect all 4 vertices together. Mine looks a lot like a lemon. Maybe yours looks better. And we are supposed to give the equation. Well, the equation is going to be x squared over a squared plus y squared over b squared, and it has to equal what? 1. Well, a is 4. What do you get when you square a 4? 16. B is 3. What do you get when you square a b? Sorry, when you square 3? 9. Still equal to 1. So other than a whole bunch of random new, seemingly, I know there's a lot of little fine details. Once you get the fine details out of the way, is it really that bad? If you're still stuck on the fine details, that's a problem. I mean, you got notes to look for the fine details. It's 3 letters of the alphabet, kids. A, B, and C. And H and K whenever it's not centered at the origin. We're going to skip to use a graphing utility. All right, so here comes an analyze. That means analyze means graph as well. That's what it means. You're going to graph it. Now, when you analyze, you think about the form x squared over a squared plus y squared over b squared equals 1. Can you figure out what a and b are? What's a? A is 5. Because 25 lines up with a squared. What's b? B is 3. How does that help you figure out c? Yeah, b squared equals a squared minus c squared. You've got something you can plug into. I didn't go over how you do that. I probably should have. It's just Pythagorean theorem. Doesn't look like a typical Pythagorean theorem, but the way that triangle was drawn on the first slide, it is. See how they drew this triangle? You'd think b squared plus c squared is a squared. And you just subtract c squared. It's based off that triangle. All right, so we plug in some stuff. That's a 9, that's a 25. Subtract 25, that's a negative 16, which is cool because we're negative c squared. Divide out your negative with your c value. Plus or minus 4. Remember, c stands for foci. And how many foci do ellipses have? 2. We actually have everything we need. So this is one that is centered along the x-axis. The center is at 0, 0. We found out that c was plus or minus 4. So where are your foci? At 4, 0 is one of them. Where's the other one? Negative 4, 0. Now, what's a give you? Vertices on the x-axis, because this is a major. The x-axis on this one is major. So you have a vertex at 5, 0. You have a vertex at negative 5, 0. A is a major vertex on this one. B is a minor vertex. Y-axis. On the y-axis, how many units you go up and down? 3. So you got one at 0, 3, and you got one at 0, negative 3. And you have everything you need to draw an ellipse. So draw your lemon or your football, whatever yours looks like. There you go. So that was x-axis major. Now it's time to do y-axis major. And here's a y-axis major. Not a whole lot actually changes. It really doesn't. Still have a center on this one since we're doing at the origin, 0, 0. Now the y-axis is what we call the major axis here because we are being cut in half by the y-axis. So the foci actually lie on the y-axis. So instead of C0 or negative C0, it's the other way around. 0C and 0 negative C. And the vertices, the letter A, the major vertices, are on the y-axis as well. So you have a 0A and a 0 negative A. Now, notice that when your major axis is the y-axis, that the major vertex is y. It's all about y. So it's no longer x squared over a squared. Y squared sits over a squared because a is the major vertex. So it changes a little bit. It's x squared over b squared plus y squared over a squared is equal to 1. Still has the same rules. A is bigger than b because it's the major vertex. They're both more than 0. And guess how you still find a squared? Sorry, I did that wrong. Guess how you find b squared? A squared minus c squared. Your vertex will always be a larger number than your foci. Always. A is always bigger than c. That's why it has to be a minus c. So there's our setup. We'll do an analyze, and the next analyze is one that you have to manipulate a little bit. It has to be manipulated. It has to be manipulated because this is an ellipse. However, no ellipse you've ever looked at has a number in front of x squared or y squared. The numbers are always where? In the denominator. So fix that part. What do? By 9. Also, ellipses are always equal to 1. So that piece has to be done. It has to be manipulated. So this gives us x squared over 1 plus y squared over 9 being 1. Now, which one of these two pieces represents a squared? 9. This is a squared. And this is b squared. The bigger number is always a squared. Always. That's how it works. So we figure out our a and we figure out our b. A would be 3 and b would be 1. Then we say that b squared is a squared minus c squared, which you can manipulate this. You can say c squared is a squared minus b squared, which works just fine. But just plug in your numbers. You're going to get something funky here. When you do 1 squared minus 3 squared, what do you get? -8, right? So 8 ends up being c squared. What's that make c? You can do a little better than that, can't you? Yeah, plus or minus 2 roots of 2. 2 roots of 2 is about 2.83 off the top of my head. But big deal is it's less than 3. Well, I guess we'll graph this one. Now, when you're graphing these things, notice the stuff with y is bigger. That's a big deal because this thing's going to be taller than it is wider. Okay, you guys understand that? Because this is bigger with y, it's going to be taller than it is wider. So we don't go left and right 3 units. We go up and down 3 units. That's where our vertex comes from. We have a vertex at 0, 3. And we have a vertex at 0, -3. How about left and right? 1. Go left and right 1 unit. Because that's what B is. And we're going to plot our foci. You can go to a calculator if you want and check me, but this is ridiculously close to 2.83. So that's just a little under 3, isn't it? It's about there and about there. And I don't even have enough room to tell you what the coordinates are anymore. It's so small. This thing is tall and skinny. Now, it's about time we be done with ones that are centered at the origin because the odds of y'all's being centered at the origin are pretty slim. especially since I told you to probably use quadrant 1. So let's jump ahead to what do you do if you're not centered at the origin? And it's really simple. Unless you're one of those kids who just never understood the whole HK notation. I mean, every transformation we ever done is like x minus h, right? Y minus k. And the way it's always been. Well, that's what we do here. That's all we do. Now, when the x-axis is major, x was sitting over a squared, wasn't it? Well, we're still going to have something squared up above it. What's it going to be? X minus h squared. Y was sitting over b squared, but up here we have y minus k. Squared was in the wrong spot. What's it still equal? 1. You do a y-axis is major, and I'll slow down for y'all. You just swap around what two letters? A and B, right? That's all you did, swap around two letters. So it's x minus h squared over b squared plus a y minus a k squared over an a squared, still equal to 1. And b squared is always equal to a squared minus c squared. Now don't let this screw up Pythagorean theorem in your head. Don't be that kid, because I've seen that happen. I've legitimately seen that happen. You do this, then you give them a Pythagorean problem, and they screw it up because they got it wrong. Too many formula for them. All right, so here's one that's not centered. We are supposed to graph it, but we're supposed to write its equation. And just like with parabolas, the very first thing I like to do is actually graph. I don't know why, but it makes it easier for me to pick out the letters. Plus, it tells me which axis is major. It really does. Some of you are got more of a brain than I do, and you can visualize this in your head. I don't have that brain anymore. When I was 16, I probably did. That was a long time ago. So I just draw because it's easy. So we have a center at 2, negative 3, to the right 2, down 3. There's my center. We have a focus at 3, negative 3. Why do they got to put things so blasted close? And a vertex at 5, negative 3. Well, here's what's cool about this. Is this one tall and skinny or short and fat? It's short and fat, isn't it? Because these 3 points are lining up on the same exact line. It's a short and fat situation, which means it's x-axis major. You guys get that? Short and fat is x-axis major. Like, that's a good note. Short and fat is x-axis major. Tall and skinny, that's y-axis. Now, I'm going to go ahead and think about the other points here. We had a focus that was 1 unit to the right. So where's the other focus? 1 unit to the left. There's another focus. So it's at what, 1, negative 3? And we had a vertex at 5, negative 3. The other one is not at negative 5, negative 3. How far apart were those x values? 3. This vertex is 3 to the right. The other vertex must be 3 to the left. Make sure you understand that. This isn't the easy ones where we just change signs and we're done with it. So we've got to be 3 to the left of 2. That puts us back at negative 1. There's your other vertex. Negative 1, negative 3. Now, getting your A's and C's is a little bit harder. Probably need to add this in here, over here. A is the distance from center to vertex. It's not the number that you see anymore because we're not centered at the origin. We can't just look at the number and say we're 5 units away from the center like we could on 0, 0. You guys get that? C is distance from the center to where? To the focus. So, you have to do some manipulation. You have to think about it. You can't just use the numbers like you did before. So we'll go back and we'll pick out A. So when we talk about A over here, we have a center at 2, -3 and a foci at 3, -3. What's the distance between those two things? 1. The distance is 1. So A is 1. We talk about the letter C. Again, we have a center at 2, -3. We have a foci, or focus. I did that backwards, didn't I? Yep. This is 5, -3, isn't it? I wrote down 3, -3. A is 3. Good catch. I had just caught it. A has to be bigger than C. So distance is 1 and A is 1. Sorry, C is 1. Oh, he needs B. What's the formula for B? B squared is A squared minus C squared. Yeah, it gets me too. So we have 3 squared minus 1 squared. That's 8 again, isn't it? So B is plus or minus 2 roots 2. Now, that means that the minor vertices are plus or minus 2 roots of 2 above or below the center. Because it's about your relationship to the center. That's what it's about the relationship to the center. And that's about 2.8, which is kind of hard to freehand graph. Really is. So I was at -3 on the center. Really, that's it, huh? Well, do what you can do. I already gave you the homework, didn't I? Do what you can do. Because when it comes to the project, like, it's not going to be as hard as this homework. You understand that, right? It's really not as hard as this homework. I don't want to spend 3 weeks going over the stuff in the project. Do what you can do. I'll fill in the rest tomorrow. That goes for you too, Riley. Hope you get well soon. Hope you don't have COVID.